Greetings and welcome all to the short course on process simulation using Dwsim. I am P.R. Naren from School of Chemical and Biotechnology, Shastra University. This is the fourth lecture in the series, and in this lecture we will see a simulation of heat exchangers. Now this is a course portal. All these presentations and assignment problems can be accessed from this course portal. Let us see what we have seen so far in the last three lectures. We have installed Dwsim. We learned to create a new simulation in Dwsim. We added components and specified thermodynamic package for the simulations that we have created. We also saw how to add material streams, specify compositions and flow rate, and obtain the various thermodynamic properties with respect to that material streams. And we saw an example of how to simulate a mixer. Now these are the things we have covered in the first three lectures, and I hope everybody is in good state to do this now independently. In today's lecture 4, what we will use is, we will use material streams and we will also use an energy stream in Dwsim. We will see how to simulate a heater, how to simulate a cooler, and how to simulate a heat exchanger. Now before we go further, let us see what is a general sequence of flow sheeting. Now any given problem statement, any given process flow sheet, in order to simulate any given process flow sheet in a Dwsim, this slide summarizes a broad overview or a sequence of procedure that one has to follow in Dwsim to do a process simulation. So we have to first create a new Dwsim simulation, then we have to use a configure simulation icon to add all the components or compounds that are required in our simulation. We have to specify the thermodynamic package based on which the calculations will be done. Then we can customize units if we require while configuring the simulation. Then in the flow sheet area of the simulation window, we have to add materials and energy streams. We have to add blocks from the object palette. These blocks are nothing but unit operations like mixing, heat exchange, distillation, absorption, so forth. Then each block has to be appropriately connected to a material and energy stream, and then we have to specify few variables or operating conditions to each of these blocks or the material streams, and then execute the flow sheet. So this slide summarizes a general overview or a sequence of procedure that one has to follow to do process flow sheeting in Dwsim. Now what is an energy stream? Now if you see in your object palette, this is usually shown in an yellow colored arrow and it is written here as energy stream. Now energy stream basically indicates how much quantum of energy is exchanged across blocks or objects in Dwsim language. Now the usual specification of the sign convention that is followed in Dwsim is, if it is positive value of energy content, then it means energy is added to a block. If there is a negative value of an energy value, then it basically denotes that energy is removed from the block. So as such, energy streams are required to either give to input or to extract energy content from a given block. Now let us take a simple example and try to learn how to do this problem statement. So the problem statement is as follows. We have to develop a simple process flow sheet to determine the heat duty that is required to heat a given fluid to a desired temperature. Now in this case, step, we can connect the heater block to the feed in, which will be connected as inlet stream. The outlet stream from the heater block will be connected to outlet, and the energy stream to the block is connected basically to energy. Now heater block can be operated in different modes. For the given question, we want to operate the calculation mode as outlet temperature, and we want to set the outlet temperature as 0 degrees Celsius. Now you will see in the drag down menu of a heater block, like heater block can be made to calculate in 4 different modes. You can either specify the outlet temperature, you can specify the outlet vapor fraction, so that means you have an inlet stream what you want as a thermodynamic state of the stream that comes out of the outer block. That can also be specified. You can specify the heat that is being added, the heat duty that is being added into the heater block, or you can also connect it in terms of an energy stream. In fact, we will specify it as outlet temperature and perform the simulation. Let me go back to my DWSIM and show how this has to be done. So, this energy stream, in line with my slides, I will just rename this as energy so that there is no confusion. So, this is a heater block, one can see on the right object palette. So, drag this heater block and leave in the process window. Now, if you single click, you can see the properties tab corresponding to this heater block. You can see this is the property corresponding to the heater block. Now, keep your mouse here and you can see a pop down window. So, there are two material streams available. Now, out of these, the inlet stream should be feed in, the outlet stream is outlet, and the energy stream is basically energy. Whatever is named here as energy should be given as the energy stream, right. Now, the moment you give all these things, the DWSIM automatically calculates and makes this in blue colored, which shows that the required number of inputs is already complete and there is already some calculation is being done. Now, in case if this does not happen also, we need not worry, because you can anyhow use these icons and run the simulation again. Now, let us go back to the calculation parameters area. We want to change the calculation mode from heat added to outlet temperature. So, we will specify the outlet temperature as 90 degrees. Keep the efficiency time being as 100. So, I have dragged a heater block into the process flow sheet, connected inlet and outlet material streams appropriately, connected an energy stream, changed the calculation mode to outlet temperature and made the outlet temperature as 90 degree Celsius. Now, once we have done this, we are ready to simulate. So, this is shown here. So, we have added a heater, we have changed the inlet, output and the energy streams and given the outlet temperature as 90 degrees. Once this is over, we can run the simulation. We have to first, if you recollect, we have to activate and then you can use recalculate all and then we can analyze the results. So, let me do it. So, I am just pressing this activate icon, then I am saying recalculate all. Now, there is no error that is being shown here. So, you can see in this information the flow sheet was calculated successfully. So, that means now we can analyze the results. To analyze the results and discuss further, so let me go back to my slides. So, we can analyze in two ways. We can see the output or the outlet or the exit stream properties. Now, the mass flow rate will obviously remain unchanged, because this is only a single operation and being energy is exchanged, there is no change in the mass content. So, the outlet mass flow rate remains at 50 kg per hour, and the temperature also as specified, it has to be 90, because if you remember, we specified for the heater block such that the heater should change the outlet temperature to 90 degrees Celsius. Now, in the heater block, you can see about 3.8 kilowatts of energy is required, or the heat duty is required to be added to the heater block, and the delta T, which is basically the difference in temperature between the exit stream and the inlet stream. In this case, it is 90 degrees Celsius minus 25, which is 65, can also be read. Now, let me show this in DWSIM. So, if you click on the outlet icon, you can see here the temperature is 90 and the mass flow rate is 50, and one can also read other properties from this window. Now, if you click at the heater block, now you can see the heat added is 3.8 kilowatts and the delta T is 65 degrees Celsius. This heat content is added to the heater block through this energy stream. So, if you click energy stream, also one can see that the heat added or the heat duty required to do this operation is 3.83 kilowatts. Now, we can report these results using build report, which is present as the icon next to configure simulation window, or we can use an insert master property table to insert the results in the simulation window. Quite often when we ask students to present results, we want the results to be readily visible next to the process simulation block diagram. So this master property table is one useful utility through which you can display the results directly in the process flowsheet window. Let me show you how to do this master property table for this present case. Now you have to click the master property table. An object property window will open. So let us say if we want to show the results of heater block. Now you have to choose heater block, and for the heater block, what are all the properties that we want to display? Now we want to display the outlet temperature, the heat added, and the delta T. So once we do this, the output can be readily seen just below the process flow sheet. So this is a process flow sheet for a heater block. Let me show you how to do this. Right. This is the master property table. So click and drag this to a point in flow sheet area. So it appears here. So just drag this and keep this below the process flow sheet window. Now you can see here in the properties tabs, once you drag this master property table into the flow sheet window, you can see the property type is material stream. We will change this object type from material stream to heater. So I will choose it as heater, and you just say activate or recalculate once. So once you press recalculate, you can see the object heat 000, which is basically the name for this heater block, appears here, and we will change this logical condition to true, and once again say recalculate. Now you can see these are the parameters that are available for us to be reported from a heater block. Now whatever the parameters we want, we can display that. For example, we want to display the outlet temperature. We want to display how much heat is added, and we also want to, let's say, find out outlet vapor fraction and the delta T. So we logical conditions, we change it to true, and then we say recalculate all, and one can see the outlet temperature is 90, the heat added is 3.8 kilowatts. Outlet molar vapor fraction is 0, which says that means the feed inlet is also in the liquid state and the outlet is also in the liquid state, and the delta T, which is basically the difference in temperature between the outlet temperature and the inlet temperature, is shown as 65 degrees Celsius. So let me go back to my slides again. So to summarize, what we have learned is we have learned how to use a material stream. We have learned how to use an energy stream. We have used a simple heater block and tried to create a process simulation of find and determine how much heat energy or heat duty is required to change the inlet, the temperature of a fluid from one given value to another given value. And we also learned how to insert a master property table into the process flow sheet. Now let us look into some of the assignment questions, and we will see how these assignment questions can be answered. Now the first assignment question is, can we modify this simulation and try to find out how much heat duty is required for vaporizing a given fluid flow. Let me read the question. So determine the heat duty required to completely vaporize 1000 liters per hour of water entering the heater at 25 degrees Celsius and at 1.5 bar. What is the temperature of the vapor generated? So the idea is you have water is flowing at, I guess, sorry, there is a typo here, this should be as 1000, sorry. So this is 1000 liters per hour. You have an inlet which consists of only water, so it is 100% water. Inlet is coming at 25 degrees Celsius and is at 1 bar, and the exit stream is at 1.5 bar, but it is completely at vapor state. Read the question. So you have to completely vaporize the incoming water at 1.5 bar. We will stick to ideal or Raoult's law formulation for thermodynamic package. So how much heat energy is required if you have to vaporize 1000 liters per hour of water from 25 degree Celsius at 1 bar. So that means you are just asking what is the enthalpy associated with vaporization of water to raise the temperature from 25 to its boiling point at 1.5 bar and then change its state from liquid to the vapor state. Now this can be easily done. If you recollect, there are different calculation modes that are available for heat transfer. We had used outlet temperature, but there is another calculation mode which is outlet vapor fraction. Now in this specific case of assignment 1, what we require is the outlet vapor fraction mode is being used, can be used, and this outlet vapor fraction mode should be changed to 1. So that means we want the entire liquid that is coming in the inlet stream to leave the heater as a vapor state. So that is what is the crux in doing simulation 1. So let me go to that slide. So we just have a simple heater block which will have an inlet, an outlet and an energy. But this heater block will be specified in such a case that it will have an outlet vapor fraction be made as 1. Now that is clearly visible in this master property table that I have got upon simulating this process flow sheet. You can see the inlet volumetric flow rate is 1000 LPH, whereas the outlet is increased because obviously the liquid has become gas, so there is an expansion, whereas mass flow rate obviously will remain the same. Now you have liquid completely coming in the inlet and that is completely changed to the vapor phase, and the temperature of the outlet which is in equilibrium at 1.5 bar is basically 111 degrees Celsius. So let us try to do, I will quickly show what is this simulation assignment 1. I will not do in detail, let me open this what I have already created. So this is assignment 1. If you see assignment 1 has an inlet stream. Now the inlet stream specifies 25 degrees Celsius, 1.5 bar, and volumetric flow rate is 1000 LPM. So let me change the unit system. So volumetric flow rate, let me change in LPH. Let me go to the process flow sheet. So I am changing the inlet volumetric flow rate as 1000. Temperature is 25 and pressure is given as 1.5 bar. Now there is an outlet stream, there is nothing to specify in the outlet stream at the beginning, there is also an energy stream. A heater is configured in such a way that the inlet stream is collected to flow in, the outlet stream is connected to outlet, and the energy stream is connected to this inlet. The calculation mode, if you carefully see, this is changed to outlet mole fraction. There are 4 calculation modes available, we have changed this to outlet mole fraction, and the outlet mole fraction in terms of vapor is given as 1. So the outlet vapor phase fraction is given as 1, which indicates that the entire incoming stream in liquid phase is changed to the vapor phase. Now let me activate and recalculate. Now you can see the results, the amount of heat that is required is 772 kilowatts is required. There is a delta T of 86 degrees Celsius between inlet and outlet. Now the same can also be visible in energy stream. You need 773 kilowatts, and the outlet is at 111 degrees Celsius, its pressure is maintained at 1.5 bar. Now you can see the liquid fraction is 0 and the vapor fraction is 1, indicating the entire liquid is being changed to vapor phase if you supply this much amount of energy. Now that completes our assignment 1. So let me take assignment 2. Now in this assignment 2, we want to simulate a heat exchanger, but without using a rigorous model of a heat exchanger. All we want to do is to use a heater or a cooler block and then simulate a heat exchanger. Now what is a cooler block? A cooler block is the one which will extract heat from a material stream with which it is connected to. Now what we have seen in assignment 1 and problem statement 1 in this lecture 4 is a heater block. A heater block essentially adds heat to the incoming material stream. So that means it raises the temperature of an inlet stream. The cooler block exactly does the reverse. So it extracts the energy content from an incoming inlet stream. So we have to use a combination of a heater and a cooler block and simulate a heat exchanger. Let me read the question. So we have to develop a simple process flow sheet to simulate a heat exchanger using only heater and cooler blocks of Dwsim, and we have to determine the heat duty and exit temperature of a stream. The data given to give this problem statement is summarized here. So we have styrene and toluene as two components. We will use ideal or Raoult's law formulation. Now one of the inlet stream is the styrene inlet stream, which is written as STYIN. The another inlet stream is a toluene inlet stream, which is written as TOLIN. Now FPS system of units or the English units is followed for this problem statement. This problem statement is adapted from Cedars product design book. So the inlet stream of styrene is at 300 degree Fahrenheit and at 50 psi absolute, and the mass flow rate is 1,50,000 pounds per hour, and it is a pure styrene. The toluene inlet is at 100 degree Fahrenheit, the pressure is at 90 psi, the incoming mass flow rate for toluene is 1,25,000 pounds per hour, and it is a pure toluene stream. The condition given is the styrene exits the heat exchanger at 178 degree Fahrenheit and at 50 psi. So if you see, pressure remains unchanged, so it is at isobaric, there is no pressure drop mentioned for the styrene stream, and styrene, which is coming at 300 degree Fahrenheit, is cooled basically to 178 degree Fahrenheit. So we extract heat from styrene stream, and whatever is the heat extracted from a styrene stream is added to the toluene stream, and we want to know how much heat is extracted if you decrease the temperature of a styrene stream from 300 degree Fahrenheit to 178 degree Fahrenheit. So that is basically this first part, determine the heat duty. If the same heat duty is given to the toluene stream, what is the temperature the toluene stream will rise to if you give the same heat duty to a toluene stream? So this is basically the exit temperature of the toluene outlet stream. Now this is how a typical process flow sheet requires. So we will have 4 material streams. So there is a styrene inlet, so there is a styrene outlet, there is a toluene inlet, and there is a toluene outlet. Now if you see the problem statement, we know the specification for styrene inlet, we know the specification for styrene outlet, we also know the specification for a styrene outlet, styrene inlet, toluene inlet, and styrene outlet. So for styrene inlet, toluene inlet, and styrene outlet, we already know the specification. Now we have one energy stream which I have named as Q stream, which is shown here. This is the energy stream in the process flow sheet. We have 2 unit operations or blocks or objects being used. One is a cooler block and one is a heater block. Now please read the problem statement carefully. Styrene is being cooled from 300 degree Fahrenheit to 178 degree Fahrenheit. So I will have a cooler connecting the styrene streams, whereas the heat that is removed from the styrene stream is given to toluene. So I will basically add a heater across the toluene stream. Now obviously the energy stream connects the energy that is withdrawn from a styrene stream, and we will supply it to the heater block, and this energy which it extracts from the styrene streams and gives to the heater block across the toluene stream results in increased temperature of the toluene outlet stream. Now if you can configure the simulation correctly, this is how a typical results will look like. So you can have styrene inlet, outlet, toluene inlet, out. So the toluene temperature is changed from 300 degree Fahrenheit to 178 degree Fahrenheit, and you can see the toluene stream which is incoming at 100 degree Fahrenheit is raised up to 254 degree Fahrenheit. Now the pressure of all the streams remain constant, and you can see all the phases are remaining in liquid, and this is basically the energy content that is available from the styrene stream and that is utilized in the toluene stream. Let me show this quickly before moving to the next assignment. So I am opening the assignment 2, which I have already made at my end. So I have basically styrene inlet. Now styrene in just a minute. Let me zoom this for a clarity. So I have a styrene inlet stream. Now if you see, the styrene inlet stream has only styrene specified and toluene is 0. So the styrene inlet temperature is specified. Let me change the units to English system of units. You can go to configure simulation button, go to settings, units, you can change this to Fahrenheit. We want pressure in PSI, we want mass flow rates in pounds. So the styrene inlet is available at 300 °F at 50 psi, and the mass flow rate is given as 1,50,000. So this is a toluene inlet stream. Now again, the toluene inlet stream has only toluene composition being specified, styrene is kept as 0. Now once again you can see the toluene is available at 100 °F at 90 psi, and the mole mass flow rate is 1,25,000 pound mass per hour. Now this is a heater block and a cooler block. Now these are available in object panel over here. So you have a heater block here, you have a cooler block here. So a cooler block is added across a styrene streams and a heater block is across a toluene stream. So if you click at cooler block, you can see the inlet stream is styrene inlet, the outlet stream is styrene outlet, and I have added the energy stream also to the cooler block. Similarly, if I show you the heater block, you can see the inlet stream to the heater is toluene in, the outlet stream to the heater is toluene out, and the energy stream is Q stream. Now how a cooler operation mode is there? The cooler operation mode is set to outlet temperature because we want to extract heat from styrene such that the styrene outlet stream is at 178 °F. So we have specified the calculation mode as outlet temperature, and the outlet temperature is specified as 178. Now if you click the heater block, on the heater block we will not specify the outlet temperature or the outlet fraction, rather we will leave it as energy stream, because it depends on this energy stream the heat should be made available to the toluene stream, and then its temperature has to be increased. So please be careful. Once again I repeat, for the cooler block the calculation mode is set to outlet temperature and we specify the outlet temperature as 178, whereas for the heater block the calculation mode is specified as energy stream, and we will leave it unspecified because it is already linked to the energy stream by here, which is shown here as Q stream. Now once you activate and recalculate, you can see the styrene outlet comes at 178, the toluene outlet comes at 254 °F, 254 °F, and if you click on the cooler block you can see that this much amount of heat is being removed, which is 2670 kilowatt is removed, and the same amount of heat 2670 is being added into the heater block. You can see in the Q stream, this is the heat exchange, this is the energy content that flows from a cooler block to the heater block, and this is 85 °C is basically the delta T across the heater, and across the cooler you have a delta T of minus 67 because this delta T is negative because styrene is changed from 300 degree Fahrenheit to 178 degree Fahrenheit. So this completes our assignment 2. So we can incorporate the object palette. You can incorporate even 2 object palette. I have incorporated 2 master property tables rather. One is a material stream table which is shown here, and another is an energy stream table or the energy master table. So 2 master tables I have inserted. So that completes the assignment 2. Let us see what is the assignment 3 for today. Now assignment 3 is to simulate the entire heat exchanger as such. Now this is a further extension from the assignment 2 what we have seen. It is essentially the same. The only difference being is we do not want to specify the exit temperature of the styrene outlet stream. Instead, we want to use a heat exchanger. Now, if you recollect in assignment 2, we have used 2 blocks, which is heater block and a cooler block. Now, instead of using a heater block and a cooler block, we want to use a heat exchanger and do the simulation. Now, we have chosen a counter current heat exchanger, and the heat load and the area are specified in the problem statement. Let me read the problem statement. To simulate the heat exchanger, to determine the outlet temperature of the fluid streams, the overall heat transfer coefficient and the thermal efficiency of heat exchanger. Now, we have the same styrene inlet and the toluene inlet streams from 300 degree Fahrenheit, 100 degree Fahrenheit for toluene. Styrene is at 50 psi, toluene is at 90 psi. The mass flow rate is 1,50,000 for the styrene and 1,25,000 for toluene. What we have as further information is this is a counter current flow heat exchanger. The area of heat exchanger is given as 300 meters square and the heat load is given as 2700 kilowatt. This is roughly the same what we have obtained in problem 2. So this is just round off to the next closest 100th place, and if we have this much amount of heat being added to a counter current flow heat exchanger of 300 meters square, is it possible to find out what is the outlet temperature of styrene and what is the outlet temperature of toluene and what is the efficiency of a heat exchanger. Now, this is how the process flow sheet typically looks. So, you have a heat exchanger object being introduced. Now, this heat exchanger object itself will take 4 streams. So, you can have styrene inlet, styrene outlet, toluene inlet and toluene outlet. So, 4 streams, 2 inlet and 2 outlet are connected to this heat exchanger. Now, there are different modes by which a heat exchanger can be calculated. We have specified the mode such that we want to calculate both the outlet temperatures by providing the area and the heat load. So, we want to calculate both the temperatures for a counter current flow direction, giving the area and the heat load to this heat exchanger. This slide summarizes the result of assignment 3. So, we will see the hot fluid outlet temperature, that means which is the styrene is a hot fluid and the exit temperature of styrene is 174, which is pretty much the same as we have taken in assignment 2. The cold fluid, which in this case is toluene, exits at 262, which is also essentially the same kind of result what we have obtained for assignment 2, and this heat exchanger configuration is about 80% efficient and it has a 30 degree roughly LMTD difference. So, let me go and quickly show you how this looks like. Let me open the solution for assignment 3. Now, what I have used, I have created 4 material streams and named them as styrene inlet, styrene outlet, toluene inlet and toluene outlet. I have used the heat exchanger. So, this is the heat exchanger object palette. So, I have used the heat exchanger object palette and connected these 4 material stream. Now, individual material stream is specified as before. So, styrene is specified inlet as 300 degree Fahrenheit, 50 psi and 1,50,000 pounds per hour. Toluene inlet is at 100 degree Fahrenheit, 90 psi and 1,25,000 pounds per hour. The heat exchanger, the inlet streams to heat exchanger is styrene inlet, toluene inlet, which are here. The outlet streams are styrene outlet and toluene outlet, which are here. Now, there are different modes by which the heat exchanger can be simulated. Now, we can use the heat exchanger to simulate both the temperature. You can use this heat exchanger to simulate only the hot temperature. You can simulate the heat exchanger in a way so as to calculate the temperature of the cold stream. You can use the heat exchanger to calculate the product of U into A. You can use the heat exchanger to calculate the area of heat exchanger, or we can also give a rigorous shell and tube configuration for this heat exchanger and simulate the heat exchanger appropriately. Now, in this problem assignment 3, what we have done is we want to calculate the exit streams for a given heat exchanger. So, we have used the option of calculate both temperature. Now, you can change the specification of flow direction in this menu. So, we have left as counter current. Now, we need not give any pressure drop. So, you can make it as 0. Give the area of heat exchanger as 300 meters square as per problem statement, and the heat load obviously has to be given. So, which is 2700 kilovolts. So, once you give this, activate and recalculate all. Now, you can see this results being updated in the master property object palette. I mean, this is the master table, that property table that I have inserted using heat exchanger as the object. So, let me go back to my slide. So, I hope you are able to get these results. So, I wish that you take time to explore the other different types of calculation modes that are available for a heat exchanger. By changing this, depending on what you change, you will be able to calculate either the heat load or the heat exchanger area or the product of overall heat transfer coefficient and to the heat exchanger area, or you can also do a shell and tube heat exchanger rating. So, please take time to change these calculation modes and then see how to use the same process flow sheet to calculate all of these. Now, if you have any queries with respect to this tutorial or in general regarding the use of DWSIM, feel free to use forums.fossee.in to raise your query. I will show you this. So, this is forums.fossee.in portal. This is managed by IIT Bombay under NME-ICT MHRD program. You can create your login. Once you create your login, you can ask any generic question on DWSIM. So, choose DWSIM category, give a short title for your question and please submit your question in this dialog block. This will be answered not only by the people from IIT Bombay, this can be answered by any interested person who works on DWSIM across the globe. So, please feel free to use this forum.fossee.in portal to raise queries on DWSIM or on this lecture as well. The lecture content, this PPT, assignments, everything is made available also at this portal. So, you can feel free to obtain this from this portal. Thank you. So, this ends the lecture flow. So, in next lecture, we will see how to simulate phase equilibrium calculation. We will see how to do reaction equilibrium and phase equilibrium. Thank you all. Thank you once again.